Have you been burned by overcooked coffee? Have you been fooled by false labeling? Because here at Cafe Legal Solutions, we get you the compensation you deserve. I don't like this, because it doesn't say anything about burning me. That's right, you deserve compensation. That's why if you call within the next 8 seconds, we'll send you not 0, not 2, but 1 free Cafe Cool. Here's how it works. You grab your favorite coffee. Stick the Cafe Cool into the coffee, blow in one end. The heat goes into the coil, and hot air comes out, leaving you with cool coffee. Here's how to order. Just call 1-800-CafeCool.com. That's 1-800-CafeCool.com. Order now while supplies last. Shipping and handling not included. Not responsible for cancer, colon malfunction, liver failure, dizziness, heart attacks, silliness, mesothelioma, or cross-eyedness. Not meant for ingestion. Do not call because this is not a real ad and you will not receive any Cafe Cool. I repeat, this is not a real ad. I think that's enough of the fake infomercial. Let's talk about how this thing actually works. This is a cup of coffee with the Cafe Cool inside. The cool air is blown through the entrance, and as the air travels through this tube, heat is conducted from the coffee through the copper tube. It's carried away by something called convection, and then it exits hotter than whenever it entered. Let's take a closer look at a section of the pipe. What we have is conduction through the wall, where heat is carried through the wall of the copper, and then convection carries that layer of heat into the air, and the air exits hotter. Okay. We'll look at conduction through studying this example right here. We've got 3 blocks of metal. The middle one is the copper that we're going to be talking about, but we've got a hot piece of metal, cold piece of metal, and something that's transferring that heat. That transfer, when they're in direct contact, that's called conduction. It flows from hot to cold. You never see it any other way. And then this Q dot, this is the heat flow. The heat flowing through the surface. Q would be the energy. Q dot just means that it's flowing over time. This is the heat conduction equation. It was figured out by a man named Fourier. He was a French man, so that's probably not how you say his name, but this is the heat. It's flowing through that body that we were talking about before. Now K, that's a constant that depends on 2 things. It depends on the type of material. So copper in this example, it could be steel, it could be wood, it could be cork, it could be anything, cotton candy. But then it also depends on temperature. So if it's a higher temperature, then you'll have a different thermal conductivity, that's what K is, than if it's at a colder temperature. So K is the thermal conductivity, which depends on the material and the temperature. A is the surface area of the contact. So we've got this top portion right here of this copper block. That's this top view. So A is that surface area. If you've got a bigger area, you have more heat flowing through it. That makes sense. And then we've got the hot temperature. So that comes from the hot block minus the colder temperature coming from the colder block, divided by the distance at the hot block minus the distance of the cold block. And that's why there's this minus sign here, because these distances go from, you could say 0 to 1 foot. I don't know, something like that. And that would be 0 minus 1, which would be a negative number. So this negative compensates for that difference. So that's conduction. Convection is very similar to conduction. We've got another copper block here for an example. And this heat flowing through, that's conducted through this body. And air is being blown over this surface right here. You can think of this as if you're standing in the wind, you're going to be a lot cooler than if you're not, as long as it's cool wind. This H determines how the air is blowing over. It doesn't have to be air, but this is just an example. So it could be any type of fluid that's moving over. This is the equation for convection. Again, we've got the heat going through the block. We've got this H that depends on how the air is flowing. We've got the surface area of this side right here, at the side that the heat is going out of. And then we've got this difference in temperature. So we've got the temperature of the block minus the temperature of the air. If you have a bigger difference in temperature, then you're going to have more heat flowing through this body. If you've got a smaller area, say, you'll have less heat flowing through the body. And this H, if it's super windy outside, you're going to be getting a lot cooler as long as that wind is cool. We've got the heat flowing through, and let's look at one section of air. So this is just one little portion of air. This is cool air. It's blowing up against this building, but it can't blow through the building. So instead, it goes up against it, and some of this heat is conducted into this air. Yeah, so fluids also have a thermal conductivity, but whenever it's blown up against something like this or moves over, it's that movement that makes it convection. So we have heat, but it's also still kind of cool, and then it heats up more and escapes the wall. The thing that makes convection so effective is that this cycle is going to keep repeating with new air coming in. It's just going to keep on coming. So we've got more air, it's just going to keep on coming as long as it's windy. Now radiation is pretty strange. It has to do with electromagnetic waves. So this is what the AI part of Google says for radiation. Heat radiation, or thermal radiation, is the transfer of heat energy through electromagnetic waves, allowing heat to travel across space without needing a medium like air or water. So it doesn't need something to travel through. For example, the sun, it radiates to Earth and heats up the Earth, but space, there's hardly anything for the radiation to go through. But it doesn't need that like conduction and convection. So this is just an example of the electromagnetic waves. It's a little strange, so I'm not really going to go into that. Okay, so those were both flat objects, but our Cafe Cool is not flat like that. We're going to look at a section. Here's a section, the top of the Cafe Cool. And looking at a top view of this, you can see the inner circumference is smaller than the outer circumference of this wall. As you can see, this inner circumference is a lot shorter than the outer circumference, which means heat, it doesn't flow directly straight. It kind of goes at an angle as it moves through the body. So that'll make a difference, but I won't talk about that much because it becomes a lot more complicated with a little bit of calculus and differential equations. And we've gone through the whole cycle. Air moves through, it's conducted. That depends on the thermal conductivity, the area that it has, the thickness of this wall, and also the difference in temperature. That's a huge factor. If you have the two temperatures the same, there's not going to be any heat flowing through it. And that makes sense intuitively. You're not going to have any heat flow if two things are the same temperature. The air, when it's passing through, it takes that heat from convection like we talked about before. So it takes that little section of air, that air heats up, and it keeps moving. But as that air heats up, it's a little bit more complicated in this situation because the air is getting more hot, so there's less transfer of heat as it goes farther. That hot air escapes, and now we have a much cooler coffee. Okay, let's see if it fits. Oh, that's perfect. Nice. What you just saw was testing out a bearing fitting into a 3D print to test for an anemometer that I'm designing right now. That's what you can see here. An anemometer measures the speed of fluid, and it's related to velocity, which I could find through angular velocity and the radius of this anemometer. You may be wondering why we need the speed of fluid. It's because it relates directly to the convective heat transfer coefficient, which is that h we saw earlier. So the velocity found by the anemometer will relate to that h. As you can see, the anemometer, if you want to call it that, can hold the bearing pretty well. But a couple things I thought of. The first one, there's hardly any load on this, so it doesn't need a bearing in the first place. And the second one is this bearing creates a lot of resistance that's not necessary. I'll show you what I mean. It stops almost instantly. Here's my solution. New bearing. You put this through, and then when you blow on it, it goes for a lot longer. A lot less resistance. So this is what I'm going to be going with. The anemometer is definitely wobbling here, so we're going to need something else. Alright, let's make a new one. It's going to be made for putting on a pin. So it's going to have a lot smaller diameter, and the blades are going to be smaller also, so that I can get a more precise radius. Using this slow-mo video, I found the velocity to be about 6 feet per second. I wanted to get a control for how well the Cafe Cool did in comparison. This is just hot water, and it took about 3.5 minutes to cool down, times 10 speed, to 145 degrees Fahrenheit. And although the next video isn't super accurate, it shows a problem that I had in my understanding of how this whole situation would work. This is times 5 speed. Look, right there. There was a huge drop in temperature. It dropped like 10 degrees. Let's see what the temperature of the refrigerator is. You're probably wondering what in the world I was just talking about. At the time that I recorded that, I had just thought of using the idea of what's called a heat sink. So I'd have a piece of metal that I store in the fridge, and when I'm ready to drink the coffee, I'd put it into the coffee, and the heat sink is where the heat sinks into that body. So the heat would be removed from the coffee, taken into the metal, and then I'd take the metal out. And that's based on the concept of heat capacity. According to Merriam-Webster, heat capacity is the quantity of heat required to raise the temperature of a body 1 degree, also known as thermal capacity. That's not super clear to me what that means, but how I think of it is how much heat a certain kind of material can hold. For example, copper has a heat capacity of about 0.4, air has about 1, and water is over 4. So copper can only hold about 1/10 of the heat as water can. And air can hold about 1/4 of the heat as water can. That means that water can hold a lot of heat. Let's look at this example of a coffee cup that I weighed, and then the room temperature is about 77 degrees, meaning the cup is also 77. And then we've got this coffee that would be in the cup. It is 300 grams at 169 degrees Fahrenheit. When you put the coffee into the coffee cup, a lot of this heat is going to go into the coffee cup. This can be written using this equation right here. So we've got the heat. Notice it's not a heat flow. This is just amount of energy. Is the mass times the heat capacity times the difference in the temperature. So if you've got a greater difference in temperature, you'll have more heat. If you have more mass, you'll have more heat. And if you have a greater heat capacity, for example, water having a much greater heat capacity than copper, then you'll have a greater heat. Now the heat capacity for our cup is around 0.9, since it's ceramic, joules per gram degree Celsius. That's the unit. So if you have 1 gram at 1 degree Celsius, it would be 0.9 joules. Joule is an energy unit. Likewise, for the coffee, we have about 4.2 joules per gram degree Celsius. Using this concept, we can say that the heat with respect to this final temperature that I want to know of the cup is equal to the heat of the coffee for that temperature that we want to know. So that's all with respect to a reference temperature. Whenever you do the algebra, solve this equation, we get that the final temperature of the coffee and the cup after the heat's transferred, that'll take some time, but after that's done, they'll be at about 147 degrees Fahrenheit, which is pretty much ideal drinking temperature for me. I want to talk a little bit about the differences between the straw and just using a coffee cup as a heatsink to take the energy out of the coffee. The straw worked okay because of the high thermal conductivity of the copper, but having a greater surface area would make it cool down a lot quicker. The problem with that is if you give too much surface area to the tube, then you won't have any room for your coffee. Not great for this situation. The heatsink, it's pretty much the way to go for any home uses. I was having a lot of trouble trying to figure out why I'd ever burn myself on coffee, because these coffee cups, they take away almost all the energy that I wanted. As I just showed you, it went to 147 degrees Fahrenheit, which is almost ideal. And I've burned myself on coffee a lot. I don't know if a lot of people do that, but I finally came up with it. I think it's because of using paper or plastic cups whenever I go places. They have cups that don't have much capacity for holding the heat, so that heat just stays inside the coffee, and then I drink it and burn myself. So for home uses, I'll probably just stick to not using any heat transfer mechanisms, just pouring the coffee in the cup, letting it transfer into the cup, and then the cream will cool it down even more. One fascinating thing to think about in this kind of situation is that the coffee, in our case, is only being poured in the cup once. So the cup starts at room temperature. It's ready to accept the heat from the coffee. But in industrial applications, say you have a hot pipe, for example, and it always stays hot, but you need to get rid of that heat. You could use a copper pipe like we did, and the convection of the fluid running through the pipe would cool the pipe down a lot quicker, because in that case there's no heat sink other than just the air that's sitting around the pipe. That's not going to cool it down quick enough for a lot of cases. Think about a radiator in your car, for example. There are a bunch of pipes, and it eventually leads through the engine and to the front where air is blown over those tubes, and through convection the heat is taken away. That's why your engine doesn't overheat. And finally, I just wanted to show you how fast the coffee, or hot water in this case, cooled down with the cream. It took only about 40 seconds, because it's 5 times speed, to get down to 145, which is what I like. I really hope y'all learned something new about heat transfer through conduction, convection, and radiation. For radiation, if you want to learn more about that, go watch the Efficient Engineers video on that. I'll put it in the description. If you've made it this far, thank you so much for watching, and consider subscribing if you want to watch more stuff like this. And not least but last, if you don't take anything else from this video, please take this. It's so cool and fascinating, wonderful to learn about all these cool concepts that we can study on this earth. But please, don't let yourself be so distracted that you don't see who created this. God created this with intention. He created you for a purpose, and don't forget that.